All right, hello everyone, and welcome to February 25th edition of the Water and Environment Student Talks. Thanks everyone for joining. As you hopefully saw the email late last week, I think, we have the West Conference in June, which is being hosted by UBC, which is open to any students who are interested in just having a conversation about water. So abstracts and posters submissions are due on April 15th, so you got about a month and a half maybe. For that, and you can also register. So there's the website, and I'll post this link in the chat in a minute as well. All right, and the WESTalks, as always, is hosted by IC Impacts and UBC Future Waters, which interestingly, our speaker today is also part of a Future Waters group, but at a different university. So our organizing committee is Abhishek, Lili, Fuhar, myself, Jaskaran, and Furia. And I'll also post the link for this. This is a super cool thing. In the last few weeks, we've been doing this, where we'll post this Padlet link down here in the chat. And if you haven't already done it in a previous week, log on, please. And then there's a red plus button in the top right corner. If you click on that, you can add in your location you're calling from. So this was as of last week where people listening to WESTalks were from over the last month or so. Okay, and now getting on to today's speaker, Dr. Dyllon Randall from the University of Cape Town in South Africa. And the presentation is titled Urine, the Liquid Gold of Wastewater. Oh yeah, and all of the previous talks are available on YouTube, which is the link for the YouTube page is in the invite email each week. Okay, and it's my honor to introduce Dr. Dyllon Randall for today's talk. So trained as a chemical engineer, Dr. Randall currently leads a team that is looking at novel ways to recover value from wastewaters. In 2018, he led the team that grew the world's first biobrick from human urine, which is very exciting. I suggest you go look that up on Google. It's quite an interesting project. And maybe we'll hear about it today, not sure. He's an associate professor in water quality engineering at the University of Cape Town and is passionate about the environment, sustainable sanitation processes, and making a positive difference in society. He currently holds the prestigious Future Leaders of the African Independent Researcher Fellowship from the UK's Royal Society. He is also the recipient of the Institution of Chemical Engineers Warner Prize for Exceptional Research in Sustainable Chemical Processes, as well as the Next Einstein Forum Fellow. And with that, I am going to stop sharing and we'll hand it over to Dr. Randall.
Thank you.
And feel free to post questions in the chat box throughout the presentation, and Lili is going to moderate the questions at the end. Thanks a lot.
Cool. Can I begin?
Yep, go for it.
So if we look at our modern sanitation system, specifically the toilet, we see that we combine our feces and our urine with good quality drinking water, only to flush it away to a wastewater treatment plant where we spend significant amounts of money and energy to remove three key nutrients, namely nitrogen, phosphorus, and potassium. But if we examine this wastewater stream more closely and we focus on the urine, we see that the urine only makes up about 1% of the total volume of the wastewater. But this urine contains over 80% of the nitrogen, 70% of the potassium, and 50% of the phosphorus. Now, these are three key nutrients needed to make any inorganic fertilizer, and we literally flush them away every day. So how about rethinking our wastewater and simply focusing on the language? For example, is this wastewater? Why not call it a resource? Should we call something a sewage treatment plant? Why not call it a nutrient recovery plant? Is urine really a waste, or is it a liquid gold? Simply by changing our language, we help create paradigm shifts in how we view these precious resources. So how can we collect the urine? Well, we could use what is called a no-mix toilet, and like the name suggests, it doesn't mix the feces and the urine, or we can simply collect it directly from urinals. And don't worry, ladies, unisex urinals do exist. The impact of urine separation on our wastewater treatment plants can be quite significant. So when we look at a typical biological nutrient removal system for treating wastewater, we see that we actually require energy. But if we were to implement source separation, we actually have the potential to produce energy because of the reduction in the nutrient load. Now we come to the resources that are actually in the urine. And we see that about 90% of the nitrogen is fixed as urea. Now this urea degrades in the presence of an enzyme called urease and will produce CO2, ammonia, or ammonium, depending on the pH of the solution. You can prevent this reaction from occurring by operating at a low pH, but we also recently showed that you can do this by operating at a high pH. But to understand this better, we have to look at the chemistry. So again, if we consider that reaction and we have fresh urine just sitting for a number of days, we see that the total amount of ammonia being produced gradually increases, meaning that that reaction is occurring. But when we add urease, so that enzyme now, it speeds up the reaction and we have a rapid increase in the amount of ammonia being produced. But when we add something like calcium hydroxide to the fresh urine, we see that we don't have an increase in the ammonia, meaning that that reaction is not occurring even though the urease enzyme is present. But it's not so much the fact that we have calcium hydroxide, but rather it's the effect the calcium hydroxide has on the pH of the solution. So it's the higher pH that is inhibiting that reaction from occurring. To understand this better, we have to understand solubility. And I'm going to give you a very simple example of sugar dissolving in water. So imagine you have a teaspoon of sugar. Imagine it's in your coffee in the morning, and all of it will dissolve when at 100 degrees. In fact, a whole jar of sugar would still dissolve at 100 degrees. You would need a whopping 4.75 kgs of sugar before no more sugar would dissolve at 100 degrees. Now, if you did this at 25 degrees, you would need only 2.2 kgs. And if you did this for a full range of temperatures, you would get this curve, solubility curve. So if you operate below this curve, you have an undersaturated solution. And if you have just the right amount of sugar, you would have a saturated solution. And if you have too much sugar, you have a supersaturated solution. And the amount of solid that remains in solution would be the difference from that point to the solubility curve. What this simple example shows us is that as the temperature increases, the solubility of our sugar increases as well. But when we look at the solubility of calcium hydroxide, we see that as the temperature increases, the solubility of calcium hydroxide decreases. Calcium hydroxide is said to have an inverse solubility curve. What we also notice is the amount needed to create a saturated solution is far less than our sugar example. What we also note is that the saturation of calcium hydroxide in urine and water, the saturation pH that is actually very similar, even though the water and the urine would have vastly different compositions. And it's fixed at a specific temperature. But what we notice also is that, so each curve here is for a different urine composition. We see that the amount needed to create the saturated solution varies depending on your urine composition. So my urine is very different to anyone else's. So to compensate for this, we recommend a dosage of 10 grams of calcium hydroxide per liter of urine you would treat. So to summarize, the amount of calcium hydroxide dissolving depends on the composition of the urine, and the saturation pH is fixed at a specific temperature. Now, this allowed us to develop this, if you like, a design chart, where we show the ideal operating region being high pH and relatively low temperatures to prevent the loss of urea from urine. This allowed us to develop a passive dosing system. And what this means is you have a container to which you add your calcium hydroxide and you add your urine. And so a small amount of the calcium hydroxide would dissolve. And if someone comes along and adds more urine to the container, a little more of the calcium hydroxide dissolves. So provided you have enough calcium hydroxide for the volume of your container, you would maintain a high pH and hence prevent that reaction from occurring and retain all the urea in solution. So this allowed us to develop a fertilizer-producing urinal. So it's very simple. It consists of a removable container, a funnel with a splashback to which we add calcium hydroxide, and then you simply add urine. So from this 25-liter container, we can produce about 280 grams of fertilizer per 25-liter urinal. And we have about a 96% phosphorus recovery as calcium phosphate. Because we're increasing the pH of the solution, we precipitate out all the phosphorus as calcium phosphate. But this also allows us, like I said before, to retain all the urea in solution because we're operating at a very high pH value. So what the simple system allows us to do is to overcome many of the challenges typically associated with urine collection. So for example, if you have an existing building and you want to install a urine collection system, you often have to retrofit the plumbing system, which can be expensive. But these urinals would be standalone. They wouldn't have to be connected to a sewer line. When you send concentrated urine through pipes, eventually the pipes can build up with solids. The irony, though, is that the solids that build up in the pipes are actually valuable fertilizers. And so what we're doing with our fertilizer-producing urinal is we're forcing the fertilizer components to form in a removable container rather than in the pipes. And then finally, waterless urinals can smell if not managed properly. And the reason for this is most often as a result of the ammonia production being produced from the stored urine. But because we prevent that reaction from occurring, we don't have issues of ammonia. Let's not forget that these urinals are also waterless, so we have substantial water savings. You could save up to 30% of an individual's water savings per day just by adopting such technologies. And as an example, the University of Cape Town uses 8 Olympic-sized swimming pools just to flush their urinals on upper campus every year. And considering that we recently came through a severe drought in Cape Town, these kind of technologies are a must going forward. And then finally, we could also produce fertilizer. So again, using UCT as an example, we require about 4 tons of fertilizer per year to fertilize our sports fields. And from the urine just collected on upper campus, so this is a map of upper campus, we can produce 7 tons of fertilizer just from the urine collected in urinals. So that doesn't even include toilets. What else could we make? So I've mentioned calcium phosphate, but we could make a wide range of fertilizers such as urea or even ammonium sulfate and a whole bunch of other things. And let's not forget that because we're making fertilizer, we can sell it. And you could sell it as a niche fertilizer. If you go to any plant nursery and you look at the prices for these kinds of fertilizers, the liquid fertilizers that you would use for your ornamental plants, they are substantial in terms of the price that you would pay for them. So let's just take an example now of how we could produce a liquid fertilizer. So imagine we take 1,000 liters of urine per day, and we send it through a reverse osmosis system to concentrate it, and we get a recovery of 80%, meaning we get 800 liters of water in this example. Now, typically with a reverse osmosis stream, you would produce water. That's your primary goal. And you would have a brine stream that is considered a waste stream. But in this process, that brine stream is the valuable product stream. It is the valuable liquid concentrate. And you could sell it for up to 800% more than bulk fertilizers if you sold it as a niche fertilizer. So this really is an untapped liquid gold. So the next steps of this process we are developing is to basically further improve the urinal, to have a filtration system to recover the calcium phosphate, and then send the remaining components through a reverse osmosis stream to produce water, which would not be the primary product stream that we would want. The primary product stream would be the fact that we're producing a liquid fertilizer. Now, once we have this liquid component that's rich in urea, we can do something even crazier with. So we can grow various things from this. We can grow biosolids using human urine. Now, to understand how this process works, we come back to this reaction. But the key now is we want this reaction to occur, but we want it to occur in a specific location. And we are after the carbonate ions in this case. So we want to form carbonate ions. And so the way we do this is we take any loose materials such as sand, we add bacteria that produce the enzyme urease, and we add urea and calcium, which would come from our urine in this case. So the urea breaks down to give us carbonate ions, which then combine with the free calcium ions to form calcium carbonate. And this glues the loose sand particles together in any shape you want. It's very similar to how calcium carbonate caves are made, or calcium carbonate shells, or even calcium carbonate coral reefs are made. Essentially what we're doing is we're taking inspiration from nature, but these are the star of the show, Sporacina pasteurii. They are high activity bacteria, they're non-pathogenic, and commonly used in these kinds of studies. And so if we do this in the shape of a brick, so this is a mold now in the shape of a typical brick, and we fill the mold now with our bacteria and our aggregate, and then we feed the urea solution, which would come from our urine, through this mold, eventually what we get is a solid brick forming. And this is exactly what we did in 2018 when we grew the world's first biobrick from human urine. Now, in the first 5 days that this article was released, we had over 142 news hits in 23 countries with over 48,000 social media shares and 248 million people. Now, if you saw that picture that I showed you, I wasn't totally happy with it, but I thought it's okay. It's just going to go on the university webpage. Little did I know that it would go viral like this. And for 3 weeks, we were inundated with queries wanting to know about this biobrick. So a lot of the questions that we get, and I'm going to just answer some of those, are how strong are the biobricks? So when we first started, we only had a compressive strength of about 0.9 megapascals. Now it compared quite well to a 40% limestone brick, but not so strong as a 20% limestone brick. By changing the aggregate mixture from not just sand, but then combining it with 50% sand and 50% grey-walkie, which is another type of aggregate, we tripled the strength. And then when we grew it longer, so rather than 6 days, we grew it for 8 days, we increased the strength even further. But we weren't still quite happy with the strength. For example, a non-facing brick is about 8.8 megapascals, and a face brick is about 14.5. But when we optimize the process even further by reducing the major issue that we have with with urine being the ionic strength of the urine and the fact that the bacteria don't like that, we are now currently sitting at 16 megapascals. But we haven't even optimized the process to its final level. So we reckon we could give it even stronger than this. And I mean, that's pretty amazing if you consider that this is a completely natural process. Another question is, because we're using urine, do the bricks smell? So the simple answer is yes, they do. And the reason they smell is because we are also producing ammonia. But when you dry the brick, and remember, we would have to dry the brick, so we leave it out at about 20-something degrees, so room temperature, and we have a fan just blowing over it, the ammonia quickly volatilizes, and within a day or so, you no longer have that strong ammonia smell from the bricks. So it quickly dissipates. The next question is, how much urine do we require? So initially we required quite a lot, right? 30 liters is substantial just to make one little brick. But bear in mind that from this, we are recovering 340 grams of calcium phosphate, and we only recover 330 grams of calcium carbonate. So 1% of that 30 liters is actually being used to make the biobrick. Everything else we can collect, we can concentrate, produce our water, and now produce a liquid fertilizer, because that concentrated stream that comes out of the process is now rich in nitrogen through the production of the ammonium from the process. So something else that we also are doing, and this is as a result of all the media attention. So AngloGold Ashanti approached us, it was the end of 2019, and they wanted to see if we couldn't grow biobricks using their mine tailings. So the picture I show you there is a mine dump or a mining waste dump where the leftover material, the solid material, basically forms this heap. And so it's a liability for mining companies. And so they wanted to look at whether they could repurpose their mining tailings into biobricks and other products. And so we started this work in June last year, and then we had COVID, and then things were delayed. But we're making some progress with it. The interesting thing with this project is that we are using copper mine tailings. And we didn't know at the time, but the bacteria we have do not like copper. And so it's been a challenge trying to get them happy to actually form any solids and form a biobrick. What we are able to do, though, is something actually even more interesting, I think. And this forms part of another project, also funded by AngloGold Ashanti. And so with tailings, you have very fine particles, which when it's a windy day, you have these toxic dust flowing into local communities. And from that picture, you can see the communities that actually live pretty much on the mine dumps or near the mine dumps. And you can imagine this toxic dust getting into the air and how they would affect the health. So the idea with this is that we could form a biocrust on the mine dump by basically suppressing the dust formation. So when the wind does blow, you no longer have the dust blowing into the community. And the picture I show you here is our attempt to solidify the mine tailings using this process. So it didn't quite work, as you can see, but the crust that forms is really promising, because even though the bacteria are toxic towards the copper tailings, we still form a crust of calcium carbonate around the tailings. And that crust is about 2 millimeters thick. We wouldn't really need that thickness if we wanted to suppress a dust or form a biocrust over the mine tailings. But for me, this is actually a really interesting outcome from this work, and it's something that we had never anticipated or thought about. Something else that we are doing is urine collection. So this is the first of its kind in South Africa. This is the new Exxaro headquarters, which is also a mining company. No relationship to the other one. It just so happens that they have implemented the first urine collection system in South Africa in a commercial building. And simply what we did through the design process was we said, this is why we would want to collect urine. This is how you could do it. So we simply divert the urine from all the urinals, collect it in the basement, dilute it, and then use it to fertilize the nearby sports fields. So there's no post-treatment. But I still think it's a promising opportunity to showcase urine collection in a commercial building. So essentially what we are doing is developing a urine treatment toolbox of sorts. So if someone wants to produce calcium phosphate, we would have a process for that. If someone wants to produce urea or ammonium sulfate, we would have a process for that. Likewise for potassium recovery, or even if you just wanted to recycle your water. What we also want to do in the next couple of years is to have an on-site urine treatment system, so a so-called living lab approach, where we are able to recycle water, produce and recycle fertilizers, potentially even produce energy, because we could use the urea to produce hydrogen and then use that for hydrogen electrolysis. And who knows, maybe even a startup. But all of this would have to incorporate a bunch of collaborations with multiple disciplines from engineering, health, sociology, and so on. But I really think it's an exciting field to be involved in. So the future of urine recycling, in my view, is imagine buildings or even your home installing these novel fertilizer-producing urinals and other urine collection systems to not only produce and recycle water and potentially even energy, but to produce fertilizer for the nearby communities for food production, and who knows, even building material from our collected urine. Essentially, future buildings will become mini resource recovery plants. So that is my vision for the future. So I leave you with this final quote. Pollution is nothing but the resources we are not harvesting. We allow them to be dispersed because we've been ignorant of their value. I just want to thank the amazing students that have been fortunate enough to supervise, because without them, none of this work would be possible. And then obviously all the various collaborators and funders. Thank you.